Welcome to the deep dive. So imagine for a second that you're handed, like, the ultimate IT mandate.
Oh boy, the kind that keeps you up at night.
Exactly. You need to deploy a virtual desktop environment for 5,000 really demanding users. And here's the catch. You have to guarantee zero downtime.
Zero. None.
None. I mean, even if an entire data center goes completely dark, the active sessions have to fail over transparently. Like, no one logging in even notices a thing.
Which is, frankly, the kind of mandate that forces you to completely reevaluate your baseline assumptions, about enterprise redundancy.
Right. And that is exactly our mission today. We are cracking open the Nutanix Validated Design for Omnissa Horizon on AHV.
It's a fascinating piece of architecture.
It really is. It's the exact blueprint required to build this insanely resilient multi-site VDI environment. We're moving past the high-level fluff today.
Yeah, we're getting into the weeds.
We are extracting the rigorous cluster sizing rules, the actual physical hardware constraints, and those operational boundaries you need to deploy this massive solution. What I absolutely love about this design is how it takes incredibly complex infrastructure and turns it into into predictable building blocks.
Yeah, predictable is the key word there. I mean, the primary value of a validated design like this is that it strips away all the trial and error.
Which is usually so expensive in enterprise VDI.
Oh, massively expensive. It provides this heavily tested operational model that is specifically engineered to absorb catastrophic hardware failures.
Without degrading the user experience.
Exactly.
Okay, so before we start throwing around rack units and node counts, we need to map out the physical topology. The design dictates this block and pod architecture.
Spanning 2 active data centers.
Right, in a single region functioning as 2 availability zones. But, and this is a big but, there's a hard boundary established right out of the gate. Network latency between the sites cannot exceed 5 milliseconds.
Which is incredibly tight.
It is. My initial thought was like, why so strict? Modern fiber can push data insanely fast over long distances.
Well, the 5 millisecond threshold is really driven by the underlying mechanics of the active storage replication.
Okay.
And the user profile synchronization. So in an Omnissa Horizon deployment that's leveraging Dynamic Environment Manager, or DEM, the system is constantly writing application configurations and user state data back to the storage layer.
Just continuously writing.
Continuously. So if your round-trip latency climbs above that 5 millisecond mark, storage I/O starts to queue up at the hypervisor level.
Meaning the physical hardware is just sitting there waiting on the network before it can actually commit the right operation.
Precisely. And the larger risk there involves data consistency during a failover.
If the primary data center goes offline.
Yeah. If Site A suddenly goes dark, the surviving site, Site B, needs the absolute latest state of every single user's profile so it can resume operations seamlessly.
Wow. Okay. So high latency means the replication lags.
Right. And that increases the risk of a split-brain scenario.
Oh, that sounds bad.
It is. It's when the secondary site spins up a desktop, but it's using fragmented or stale profile data.
So the data centers have to be physically close enough to commit synchronous writes instantly, under 5 milliseconds, but geographically isolated enough that, say, a regional power grid failure doesn't take both of them offline.
Exactly. It's a very delicate balancing act.
And that strict constraint really heavily influences the active deployment model they outline here. So instead of an active-passive setup, where you have, I don't know, millions of dollars of compute just sitting idle, waiting for a disaster.
That nobody wants to pay for.
Right. Instead of that, both sites handle 50% of the active capacity. So you have 2,500 users routed to Site A and 2,500 routed to Site B.
Both data centers are fully operational. They're handling active sessions, but they are provisioned to instantly take on the full 5,000 user load if the other site drops offline.
You know, thinking about the architectural logic of that, it reminds me of a massive high-end restaurant.
Okay, I like where this is going.
Imagine a restaurant operating 2 identical, fully staffed kitchens on opposite sides of the building. Half the dining room gets their food from Kitchen A, half from Kitchen B.
Makes sense.
Now, if Kitchen A suffers a massive gas leak and has to shut down immediately,
the incoming orders instantly reroute to Kitchen B.
Exactly. Kitchen B already has the prep stations running, the staff is in place, they have the thermal capacity to double their output on the fly.
Yeah.
The routing logic shifts, but the diners out front, they never experience a delay in their service.
That is a great analogy, but That operational model requires really rigorous separation of duties to actually function efficiently.
You can't just throw everything into one big pile.
No, absolutely not. The blueprint explicitly divides the physical hardware into two distinct categories. You have your management clusters and your workload clusters.
The brains and the brawn.
Exactly. The management cluster operates as the control plane. It's hosting your Horizon connection servers, Active Directory, Prism Central, the SQL databases.
Okay, so that's the brains.
Right. And then the workload clusters handle all the heavy lifting. That's where the actual Windows 11 virtual desktops live.
The logic there is incredibly sound. You're isolating the control plane from the really variable compute demands of your end users.
Yeah, because users are unpredictable.
Highly unpredictable. Like a finance user running some poorly optimized macro-heavy spreadsheet on a virtual desktop, they should never be able to consume the CPU cycles that the connection servers need to process enterprise logins.
Right. Separating those failure domains guarantees that compute contention on the workload side cannot destabilize the foundational infrastructure that's managing the whole environment.
Okay, so let's translate that philosophy into physical hardware. Because honestly, theoretical designs often fall apart when you actually try to rack and cable them in the real world.
Oh, but don't they always?
Yeah. So the blueprint specifies that each data center gets a dedicated 4-node management cluster, utilizing hardware like the Nutanix NX1155 SG10 nodes.
Which is a very specific, optimized hardware profile.
Right. And those 4 nodes house the entirety of the control plane, and they fit perfectly neatly into a single physical server rack.
A 4-node configuration is perfect because it gives you that necessary N+1 redundancy for the control plane without massively over-provisioning.
Because management components don't need wild amounts of CPU density.
Exactly. They require extreme uptime and rock-solid storage reliability, but not raw compute power.
But the workload clusters, that's an entirely different story. This is where the design enforces a really strict limitation, a maximum of 16 nodes per workload cluster.
Yes, 16 nodes. Hard stop.
Now, see, if I'm the architect for a massive enterprise, my gut instinct is to consolidate. Like if I have the budget and the data center footprint, I want to build a 32-node or a 64-node mega cluster to pool all my resources efficiently.
Yeah, a lot of people think that way.
Right. Artificially capping the cluster size at 16 feels a little counterintuitive to scaling.
It feels counterintuitive until you factor in lifecycle management.
The dreaded updates.
Exactly. Massive clusters create an unacceptable maintenance burden. This design caps workload clusters at 16 nodes, specifically to guarantee that software and firmware updates can be fully executed within a standard 16-hour weekend maintenance window.
Okay, let's unpack the mechanics of that. When the Nutanix Lifecycle Manager performs a rolling upgrade,
it's a serialized process.
Right. It has to evacuate all the virtual desktops off a single physical node, push the firmware or hypervisor update, reboot the server, verify the cluster health, and then, and only then, move to the next node.
And that serialization just takes time.
So if you build a 32-node cluster,
upgrading the hypervisor across that entire cluster sequentially could take 24 to 30 hours.
Wow.
Yeah. You would completely blow past your weekend maintenance window. You'd be pushing critical infrastructure updates straight into active Monday morning production hours.
Which is a resume-generating event.
Truly. The 16-node limit is basically a guardrail for operational sanity.
It's a fascinating constraint because it forces the architect to prioritize maintainability over just raw, unbridled scale.
Absolutely.
And the constraints get even tighter when we look at the thermal footprint. The design actually mandates that a 16-node workload cluster using the high-density NX3155 G9 nodes must be split across 2 separate server racks.
Because high-density compute generates an immense, just staggering thermal load.
Yeah. A single rack fully populated with 16 of these specific nodes will draw well over 10,000 watts of power.
Which is wild.
It's a massive amount of energy. The cooling requirements for a continuous 10-kilowatt draw in a single rack would completely overwhelm the HVAC design of most standard enterprise data centers.
It would literally bake the equipment. So by splitting the 16 nodes across 2 racks, 8 nodes per rack,
you distribute the thermal load to a much more manageable 5,000 watts per rack.
Exactly. And furthermore, this dual rack deployment allows you to physically separate your top-of-rack network switches.
Oh, that's smart.
Yeah, it ensures that a single localized power distribution failure, like a PDU blowing out, doesn't sever the entire cluster's network backbone.
Okay, let's run the capacity math for the architects listening who actually need to justify this hardware footprint to their finance team.
Let's do it.
So the validated design tests this architecture using a standard knowledge worker persona running Windows 11.
Right.
Each non-persistent virtual desktop is provisioned with 4 vCPUs and 6 gigabytes of memory. Given those parameters, the documentation states that each physical node can comfortably host 100 virtual machines.
The math is straightforward, but, and this is a big but, the implementation relies entirely on the N+1 resilience formula.
Meaning you never actually provision a cluster to operate at 100% capacity.
Never.
Looking at the 85% threshold rule associated with that, my initial thought is, well, we're leaving a significant amount of money on the table here.
It looks that way, sure.
Because in a standard data center deployment, I want to run my hardware hot to maximize my ROI. If I'm strictly capped at 85% utilization, I am essentially stranding 15% of my expensive compute power.
But you're not stranding it. You are actively reserving it for disaster absorption.
Okay, explain that.
In a 16-node cluster, you only ever run active workloads on 15 nodes. That 16th node, the +1, is your distributed failover capacity.
So it's an insurance policy.
Exactly. If a node suffers a critical motherboard failure, the hypervisor needs immediate available compute resources to restart those 100 orphan virtual desktops.
Right. They have to go somewhere instantly.
Well, if you run the cluster at 95% utilization, the surviving nodes simply lack the overhead to absorb that sudden load.
And then what happens?
Yeah.
The hypervisor would start aggressively ballooning memory and heavily throttling CPU cycles just to keep the VMs breathing.
Yes, which immediately destroys the desktop experience for every single user on that cluster.
Yeah.
Performance just degrades across the board.
Nobody wants that. So relying on the N+1 math, 15 active nodes hosting 100 virtual desktops each yields a usable capacity of 1,500 desktops per cluster.
Exactly.
And since the initial mandate requires supporting 5,000 users during a total data center failover, we just divide 5,000 by 1,500.
Which means you need 4 workload clusters per site.
Right. 4 clusters, providing 1,500 usable VMs each nets out to 6,000 total capacity. So we have safely covered the failover requirement with a very comfortable 1,000 desktop buffer.
So now you have a fully predictable, validated hardware footprint, 4 16-node workload clusters, and 1 4-node management cluster distributed across 9 total racks per data center.
It's beautifully systematic. We had provisioned enough hardware to absorb 5,000 users in a full crisis. And here's where things get really tricky, because these Windows 11 desktops are non-persistent.
Ah, yes. The data problem.
Right, meaning the virtual machine is completely destroyed and rebuilt from a gold image the second a user logs off.
Yeah.
We've just introduced a massive data orchestration problem. Where do 5,000 user profiles, application settings, and browser histories actually live if the compute environments keep vanishing?
This is honestly the core profile management challenge in modern VDI, and the blueprint solves this by integrating Nutanix file storage to actively support Omnissa Dynamic Environment Manager and app volumes.
So DEM steps in and intercepts the login process.
Right.
Before the Windows desktop even finishes rendering for the end user, DEM reaches out to the file share, pulls down their specific user profile, and maps all their network drives.
And concurrently, app volumes dynamically attaches virtualized applications to the session.
As if they were natively installed on the C drive.
Exactly. But the scale of the storage required to support that process across 5,000 concurrent logins is immense.
The design specifies that the file setup handles up to 4,000 concurrent connections, utilizing anywhere between 3 and 16 file server VMs or FSVMs.
And the critical architectural decision here is determining where to physically deploy those file server VMs.
Because you're constantly balancing storage performance against failure domains.
Right.
It is so similar to organizing the logistics for a massive hiking expedition.
Okay, lay the analogy on me.
You have 2 options for managing the really heavy gear. Option 1. You force the hikers, which in this model are the workload clusters, to carry their own heavy supply backpacks.
So you deploy the file storage directly onto the workload clusters themselves.
Exactly. The system becomes entirely self-contained. But the overhead of running those distributed file servers consumes CPU cycles and storage I/O that would otherwise be dedicated to running the virtual desktops.
Right. The storage overhead physically slows them down. It reduces your overall desktop density per node.
Exactly. Now, option 2, you pool all the heavy gear into a central, heavily fortified vault. So you deploy the file storage centrally on the management cluster.
Which completely removes the storage processing penalty from the workload clusters.
Yes, maximizing their compute density.
Yeah.
But you have just created a massively consolidated failure domain.
The single point of failure.
Right. If the central vault goes offline or the door gets stuck, none of the 5,000 hikers can access their gear.
It's a tough call, and the blueprint does not prescribe a single correct approach for the file's deployment. It forces the architect to calculate their own organization's tolerance for isolated performance degradation versus centralized total outages.
And when a massive outage actually does happen, when data center A goes totally dark and a panicked user attempts to log in at data center B, how does DEM guarantee that the profile pulled from the secondary storage cluster is perfectly identical to the one they were just using?
That is where the architecture relies on VDI sync and SmartDR to handle the active replication.
Okay.
The mechanics of resolving split-brain data collisions are highly sophisticated here. VDI sync doesn't just, blindly copy files back and forth.
Right.
It actively manages the state of the profile. It ensures that only one data center location is writable at any given moment by literally locking the active data store.
Oh, wow. So if a user connects to site B,
The storage controllers instantly pivot the writable state. It ensures the user accesses a perfectly synchronized desktop without any risk of two sites attempting to write to the same profile simultaneously and corrupting the whole state.
okay, so we now have the dual data center pod architecture laid out. We have the N+1 compute constraints mathematically modeled, and the profile data is actively replicating across the sites.
The heavy lifting is done.
The complexity of this infrastructure is just staggering. But moving to the operational side, how does an IT engineering team actually maintain visibility over a sprawling multi-site hyper-converged environment so that, a minor localized issue doesn't cascade into a catastrophic blackout?
Well, visibility at this kind of scale requires a totally unified control plane. Prism Central serves as the global monitoring and management layer across both data centers.
Right.
It aggregates telemetry from every single node and enforces the operational thresholds.
Now, we previously discussed the 85% rule for overall resource utilization to protect that vital failover buffer, but the design includes a secondary, highly specific threshold for the Windows 11 virtual machines themselves.
The 5% rule for CPU ready time.
Yes, and ready time is one of those metrics that constantly gets misinterpreted as processor speed.
Oh, all the time. But it is not a measurement of execution speed. CPU ready time represents a hypervisor scheduling penalty.
It's basically the percentage of time the virtual machine is actively demanding CPU cycles. But the underlying hypervisor scheduler forces it to wait.
Because the physical processor cores are already busy executing other tasks.
Right. It's a pure metric of resource contention resulting from vCPU oversubscription.
Exactly. If CPU ready time creeps above 5%, the physical hardware is actively bottlenecking the virtual workloads.
And from the user's perspective, this immediately manifests as interface lag.
Oh, yeah. They click to open an application, and the system just hesitates. They scroll through a PDF document, and the screen tearing is super visible.
Which is agonizing. And in a VDI environment, user experience completely defines the success of the deployment. Consistently high ready time destroys that experience.
It really does. So Prism Central is constantly monitoring that scheduler contention. If the 85% utilization threshold is breached or the 5% ready time limit is exceeded, the system triggers an automated alert.
And the primary notification channel outlined in the design is SMTP, sending standard email alerts directly to the IT Operations Center.
Which is standard practice.
It is standard practice. But a critical dependency like that requires a fallback mechanism, right?
Oh, 100%. The obvious flaw in centralized alerting is the vulnerability of the control plane itself. If Prism Central crashes or loses network connectivity, your primary alerting engine is just dead.
Right. Who watches the watcher?
Exactly. The blueprint mitigates this by configuring redundant alerting at the Prism element level.
Oh, so the individual clusters.
Right. The underlying Nutanix clusters themselves are configured to send fallback SMTP alerts directly to a secondary operations mailbox.
So during normal operations, the engineering team configures routing rules to just ignore those to prevent duplicate alerts, spam?
Yep. But if the central pane of glass shatters, the individual clusters still possess the autonomy to broadcast critical hardware failures.
I love that. And we also have Nutanix Pulse running in the background.
Yes. Pulse acts as a continuous telemetry stream. It sends localized cluster health data back to Nutanix for automated remote diagnostics.
Which allows their support engineers to detect known firmware anomalies or impending hardware degradation before they trigger a system-wide failure.
It really highlights the operational distinction between reactive event monitoring and proactive performance management.
Let's break that down.
Event monitoring is the fire alarm. A memory bank fails, the system generates an alert, and an engineer dispatches a replacement part today.
Great, it's immediate.
But performance management is analyzing the telemetry stream over the past 12 months. It's tracking storage I/O growth, network bandwidth saturation, CPU utilization trends.
Looking at the long game.
Exactly. It enables an architect to look at the data and definitively state, based on our current onboarding rate, workload cluster 3 will exhaust its compute capacity in exactly 4 months. We need to procure and rack a new block of nodes this week.
You absolutely need the fire alarm, but you also desperately need the meteorologist predicting the long-term weather patterns.
Perfectly said.
So if you are the architect tasked with designing this on Monday morning, the ultimate takeaways from this validated design really center entirely on discipline boundaries.
Discipline is everything here.
Deploying 5,000 highly available desktops isn't just about securing an unlimited capital expenditure budget. It is about strictly capping your clusters at 16 nodes to ensure lifecycle management doesn't break your weekend maintenance windows.
Right.
It is about aggressively protecting that N+1 failover buffer. It's about managing hypervisor scheduling to keep CPU ready time under 5%. And it is about relentlessly splitting your workloads across isolated racks and disparate data centers to neutralize those failure domains.
It really is the architectural embodiment of meticulously engineering for the absolute worst-case scenario. Adhering to a validated design shifts the infrastructure from a custom-built, fragile environment to a highly predictable, incredibly resilient platform.
Predictability at scale. Now, before we wrap up, I want to leave you, the listener, with a critical vulnerability to analyze regarding that predictable environment. We discussed how the entire event monitoring safety net, the centralized fire alarm for this massive infrastructure, relies really heavily on SMTP alerts firing off to the operations team when a critical threshold is breached.
A standard, universally adopted communication protocol for IT operations.
Standard, yes. But consider the underlying dependency. What if your enterprise exchange server or your mail routing gateway is virtually hosted on the exact same Nutanix infrastructure that just suffered the catastrophic failure?
Oh, man.
Right. If your infrastructure alarm system relies entirely on the processing power of the grid it is actively monitoring, how will you ever receive the alert when the entire cluster goes dark?
It is a sobering circular dependency that, honestly, architects often overlook until it is way too late.
A broken bone on an X-ray is easy to spot. But in enterprise architecture, identifying the hidden fracture before the system collapses under pressure, well, that is the actual job. Thanks for taking this deep dive with us.